Okay. So I'm Clifford Idumwa 2425400627, and this is Group 7, Computer Architecture. And we are presenting on understanding input outputs in computer architecture. In computer architecture organization, input output in brackets IO refers to the mechanism and the processes that allow computer system to interface with external devices such as keyboard, mice, display and storage devices, and network interface. IO is a critical for embedding communication between computer internal components, CPU, memory, and other outside world. So for me.
Okay, next slide. Okay, my name is Debbie Richard. Index number 24254000576. I'm explaining input. When you say input is data or instruction received by the computer from external device. External device like keyboard input, sensor data. And when we come to output also means data or results sent from the computer to the external device. And also example is monitor, rating to the disk, and many more. And another one is input-output device. These are hardware components like keyboard, printers, and disks, network card, and facilitated input and output. And another one is input-output operation. This process the reading into brackets input or written output data from this device. Okay, next person should continue from you.
Eugenia, this one.
Okay, so we are going to talk about my name is Eugenia Appa, and today I would like to talk about the input-output system components. So with the I/O devices, they are categorized by function. Example, human readable like keyboards, machine readable like this, or communication like network interfaces. We have the I/O controller, a hardware component, example, USB controller, disk controller, that manages communication between the CPU or the memory and I/O devices. It handles low-level operations like signaling and data transfer. We also have the bus. A bus is a communication pathway. An example is the PCI Express. That is the peripheral component interconnects express. We have the USB that connects the I/O devices to the CPU and memory. Then we also have device drivers. It's the software that provides an interface between the operating system and I/O devices, translating high-level commands into device-specific operations. The next person will take it from here.
Okay, so my name is Nana Oseko Asante. Index number 24254037772. And I'll be presenting on I/O techniques. So I/O operations can be managed in several ways, each with trade-offs in performance and complexity. Number one, programmed I/O into brackets polling. The CPU actively checks the status of the I/O devices to determine if it's ready to transfer data. Simple but inefficient, as the CPU is occupied during polling. Number two, interrupt-driven I/O. The I/O device signals the CPU via an interrupt when it's ready to send or receive data. More efficient than polling, as the CPU can perform other tasks while waiting. Number 3, direct memory access. A specialized controller, into bracket DMA controller, transfers data directly between I/O devices and memory, bypassing the CPU. Ideal for high-speed, large data transfers. Example, disk I/O or network data. Number 4, memory mapped I/O. I/O devices are mapped to specific memory addresses, allowing the CPU to communicate with devices using standard memory read or write instructions. Simplifies hardware design but requires careful memory management. Performance considerations. Latency. Latency is the time taken to complete an I/O operation. Throughput. Throughput is the amount of data transferred per unit of time. Buffering and caching. Used to reduce latency and improve throughput by temporarily storing data in memory. I/O scheduling. Algorithms, for example, FCFS and SSTF, to optimize the order of I/O requests, especially for disk access. Interrupt versus polling trade-offs. Interrupt-driven I/O reduces CPU overhead, but introduces interrupt latency. I'll hand over to the next person.
Please, who is taking over?
Who is using this one?
I/O in modern architectures. I/O buses. Modern systems use high-speed buses like PCLE, Peripheral Component Interconnect Express, faster data transfer. Storage systems. SSDs using NVMe and HDDs rely on advanced I/O controllers for high performance. Network I/O. Network interface cards, NICs, handle high-speed communication with low CPU overhead using DMA. Virtualization. Virtual machines use virtual I/Os with hypervisors, managing access to physical I/O hardware. So now I'll hand over to the next person to continue.
Salamatu Suleimani, index number 2425400609. I'll be taking the challenges in I/O design. Scalability, handling increasing members of devices and data rates. Security, preventing unauthorized access or data breaches via I/O devices. The next one is compatibility, supporting diverse devices with varying protocols. And power efficiency, minimizing energy consumption in I/O operations.
My name is Apa Okwabena Kelvin, index number 2425402430. Examples in practice. When a key is pressed on the keyboard controller sends an interrupt signal to the CPU. This interrupt notifies the processor that a new input data is available. The operating system then takes over processing the keystroke and responds appropriately, such as displaying the character or executing a command. DISC input or output. During DISC operations, the system can utilize a direct memory access, that's the DMA, control to transfer from a solid state drive, SSD, to a main memory. This process occurs without direct CPU involvement, allowing the processor to perform other tasks whilst the transfer is handled independently. Graphic output. In terms of this display output, the graphic processing unit, that's the GPU, is responsible for rendering images and frames. These rendered frames are then transmitted to display through a high-speed communication interface such as PCI Express. This offloads graphical computations from the CPU and ensures smooth visual performances. Thank you.
You are done.